So recall, the calculations that I'm about to go over are not on your quiz next time. Although sometimes explaining things in terms of math helps people understand them better in terms of everything else. So if I go to my first slide here, the speed of light, let's start at the bottom bullet point. You hopefully saw that on the POGO packet. It is a constant, 3 times 10 to the 8th meters per second. I was mentioning to one of the groups the most famous equation in all of science, equals mc squared. That c is the speed of light. That Einstein equation deals with the speed of light. We will talk about that equation at the very end of the year, because it actually has applications to nuclear chemistry. But the speed of light is a number that we're going to start to use in mathematics. By the way, we would give you that value. So that value is not one that you have to memorize. A couple other things I need to bring up. One of the equations that we're going to use requires that we know a couple new variables. Wavelength. You've been drawing waves of light. Unfortunately, when it came to writing equations, we ran out of English letters after a while. So we had to start using Greek letters instead. Lambda, which is this symbol right here on the board, that is the symbol for wavelength. Now I do mention on here that the units of wavelength depend on the size of the wave. You saw for yourself firsthand different waves, different sizes. However, there's a blank that you're going to fill into your notes right now. A conversion that we need to know in order to do our light math is converting from nanometers into meters. How many nanometers are in a meter? 10 to the 9th. Nano 9, so 10 to the 9th power nanometers in 1 meter. Remember, nanometer is tiny. You drew up on your sheet of paper really long waves, but we did this ridiculous scale so we could actually see those waves. Wavelength is a property of light. Longer waves, low energy, shorter waves, higher energy. You saw that on your board diagrams. Frequency. This looks like the letter V, but it's actually the Greek letter nu. The letter V has been taken by physics for velocity. Frequency is how often something occurs. The unit for frequency is hertz. If, ladies and gentlemen, you have a radio in your car and you're not just doing like Pandora or something like that, you're actually going to one of the local radio stations. For example, WIBA is 101.5. That 101.5 actually has a unit on it. So some radios show the unit after that number. That unit is a capital M and then HZ. It stands for megahertz. 101.5 is the frequency at which they send out their signal to be picked up. When you tune a radio to different stations, I'm doing a dial, but that's a little old. When you push a button to tune to a different station, you are picking up different frequencies of that form of light. And then your antenna grabs it and plays the music that that signal is being sent out on. So hertz is actually a unit that you have in your automobile. Or if you have a stereo at home. It's just not one that we've ever really thought of before. We just, turn into 104.1. Okay, fine. But there's actually a unit after that. It stands for the frequency. So page 1 of slides is to remind you of 3 things that the first equation is going to show you. Wavelength, frequency, and speed of light. Okay? Here's the first equation that you need to know. Now, when I say need to know, I will give you that equation on a quiz or a test. You have to know how to use that equation. What that equation says is C, the speed of light, equals to wavelength times frequency. However, we typically in this class are not going to be solving for the speed of light because that's a known value. We will usually solve for frequency, which is the thing that looks like a V, but it's actually the Greek letter nu. Algebraically, you need to be able to manipulate that equation to solve for nu, because that's what we'll be plugging into. Does anyone know what nu, this V letter, would solve for if you isolate the variable? John?
Would be the speed of light divided by the wavelength.
C over lambda, yeah. This equation up on the board is the one that we're going to give you on quizzes and tests. However, you're not going to solve it in this format. You're going to solve for the frequency, what's new. In order to help you out with that, I'm going to be greeting you when you start to come in with what's new. When I ask you what's new, I do not want to know about your day. When I see you on Tuesday, when I ask you what's new, I don't want to know about your weekend. All I want to know is what's new. It's C over lambda. And I want this to be how we greet each other for the rest of our lives. I ran into a student that I student taught. So I student taught in early 2000s. I ran into this student on State Street like 8 years later. And she said, hey, Mr. Rotzenberg, what's new? So I started talking about the fact that I'm teaching in Wanakee and this and that. She's like, Mr. Rotzenberg, you're supposed to say C over lambda. There's a couple of students. I know Riley Collins is one. Logan Renish is another one who every now and then try to trip me up on this. But they'll ask me what's new. So you can feel free to try to trip me up with this as well. If I'm at Piggly Wiggly's, my kids, and you see me, you ask me what's new. I'm not going to talk about my day. I'm going to say this. Everyone around us will have no clue what in the world we're talking about. This is our way to remember how to isolate the variable and solve for frequency, because that's typically what we're going to be doing. Now, here would be a somewhat simple problem that we could do for that. I could give you a wavelength in any unit of distance, and this one's centimeters, and I could ask for the frequency. So, hopefully there's a little bit of space underneath this slide. I'm going to switch over to the Smart Notebook and show you how to solve this problem. I was given a wavelength of 4.257 times 10 to the negative 7th centimeters. In order to get that speed of light equation to work, we have to be in meters. So even though I give you the equation, you have to be the one that understands you have to start with a metric conversion. There's 100 centimeters for every meter, and that's something that you do need to remember. Since the 100's in the denominator, I'm dividing by 100. That means this gets me 4.257 times 10 to the negative 9th meters. Once you have your wavelength in meters, now you can solve for what's new. Tyler, what's new? C over lambda. C is the speed of light, 3.00 times 10 to the 8th meters per second. Lambda is the wavelength given to me in that problem, 4.257 times 10 to the negative 9th meters. Be careful when you do calculations like this. Scientific notation's in the denominator. I would highly recommend putting parentheses around all this when you type it in your calculator, or else it's going to give you that order of operation mistake that happens with mole conversions also. Oh, by the way, remember, mole conversions is on that quiz on Tuesday. When I solve this, typically I will base sig digs not on the constant C, but on the measurement given to me to start the problem. So that's why I'm going to, well, what the heck, let's base it off of C for this one, 7.05 times 10 to the 16th hertz. I mean, the speed of light is a measured value, I suppose, so. Again, hertz HZ is the unit for frequency. Frequency just refers to how often does it occur. Notice that why did I have to convert to meters? Because I have meters in my speed of light and I have meters in my wavelength. The two have to cancel each other out. You'll be given that equation. You have to know how to use that equation. Is there questions on this first part? I'll go back then to the next slide. So we just solved this one. Second equation is E equals H times nu. E stands for energy. Well, you can ignore the word quantum if you want to. It's just a fancy word for an amount. In order to solve this second equation, there's another constant that we're going to be working with. That constant is called Planck's constant. 6.63 times 10 to the negative 34 joules seconds. That number will be given to you. You don't have to memorize it. That second equation, E equals h times nu, will be given to you. You don't have to memorize it. Once again, V, which is actually nu, it stands for frequency. The point of this equation is to solve for how much energy is involved with different forms of light. So if I give you a frequency, like if I gave you 101.5 megahertz, going back to the radio station example, you could actually plug that in for frequency and solve for how much energy is given off from that broadcast. Well, cool, 101.5 is rock and roll, so there's a lot of energy given off of that, right? Not even a chuckle from you guys. Come on. I know it was lame, but give me a break here. This is all I've got. So that was a little bit better. Laugh because you're making fun of me. Fine. Okay. What this equation represents. Hopefully you saw in that POGO packet that different forms of light give off different amounts of energy. We can calculate that amount of energy. That energy required to make an electron jump up and then fall back down. Remember, an electron is attracted to the nucleus because electrons are negative and protons are positive. Higher energy, like in the color spectrum, your BIV, your blues and violets, or your invisible, your ultraviolet, your gamma rays, your X-rays. Higher forms of energy will require a lot of energy to move away from the nucleus, and then they fall back down. Lower forms of energy don't require as much. Here's another calculation that we can do. So again, hopefully there's a little space in the bottom there. Determine the energy in joules of a photon whose frequency is 3.55 times 10 to the 17th hertz. So again, I'm going to go over to the Smart Notebook. And in this particular problem, it gave me, it wants me to solve for energy, which energy is Planck's constant times frequency. Planck's constant is a known value. It will be given to you. So you don't have to memorize it. The frequency in this problem is 3.55 times 10 to the 17th. Chemistry occurs on such a small scale that we deal with tiny numbers at times. We have to get used to that. When you multiply these two numbers together, it's going to give you a tiny number for a final answer. Final answer I have for this one is 2.35 times 10 to the negative 16th joules. That capital J for joule is the international unit of energy. So on the PowerPoint slides on the very bottom of what you have, I say just like a calorie, a unit of energy is a joule. So when I drink my Mountain Dew every morning, there's calories written on it. That's the amount of energy involved in that. We'll actually talk about where that energy comes from during the course of this year. But when we solve for hours, we are giving the capital J as our final unit. So what the notes were meant to do was show you two new equations that you have to navigate through. What I'd like to end class with is going back to that previous problem for a second. Okay? Because what you will most likely see is I will give you a wavelength, because remember, here is a wavelength, and you'll have to solve for how much energy is that wavelength. Or I could give you a color. So better yet, I'll give you a color right now. Violet. Violet has a wavelength around 400 nanometers. I can ask you to solve for how much energy is in that violet color. That would require both equations. Because if I'm giving a wavelength, first thing I would do is solve for the frequency. Kagan, what's new? C over lambda. However, my lambda, my wavelength, has to be in meters. So I would take my 400 nanometers and convert it into meters. That would give me 4.00 times 10 to the negative 7. So step number 1 is convert my wavelength into meters. The unit has to be to make the equation work. Step number 2 is, well, let's plug into that equation. This step right here, sorry that I'm moving a little awkward here, is 7.5 times 10 to the 14th. That would be the frequency, the new value. If my original question was, hey, here's violet light, how much energy is given off? Step number 3, so after metric, after what's new, is E equals H times nu. Planck's constant, 6.63 times 10 to the negative 34, multiplied by 7.5 times 10 to the 14th. If I do that to finish this problem, if I do, actually it's 7.50, 3 sig digs, I would get 4.97 times 10 to the negative 19 joules.